Okay, let us finish up this problem calculating pH values at different points in a weak acid strong base titration. We are up to part C. If you want to know how to do parts A and B, that is in part 1. And here we want to know what is the pH before any base is added. Well, we know how to do that problem. It's just a simple look at the acid part. Okay, that's in the Erlenmeyer flask, and we can figure out the pH if we have 0.100 molar acetic acid. I think that's all we need, actually. We don't need the volume. This is part C. You know, when we have acid in water, we have that equilibrium, HC2, H3O2, plus water, goes to H3O plus, which we want, because we're going to get the pH from hydronium, plus C2H3O2 minus the conjugate base. We are doing an ice table. Again, this is before any base was added, so we're not even concerned about this being a titration. It's just what is in the Erlenmeyer flask before the titration starts. Right? There's an acid in there. Well, anyway, our concentration is 0.100 molar. Water doesn't factor into the Ka expression. We start out with 0 and 0. Okay. Now, obviously, autoionization, there is some H3O plus, but it's negligible based compared to what's going to happen when this dissolves and dissociates. Okay, when it does dissociate, we're going to lose some of the acid and convert it into the conjugate base. So minus x and plus x, the same values. And this is also plus x, right? For every 1 molecule of acid we lose or consume, we get 1 molecule of H3O plus, 1 molecule of the conjugate base. And then equilibrium values are these. And we have a Ka of 1.8 times 10 to the minus 5. Okay. If you're doing this and you still need a lot more practice, you feel, then go ahead and write out the Ka expression. Ka equals the concentration of H3O plus times the concentration of the conjugate base divided by the concentration of the reactant or the acid. But I'll just plug in the x's right now. And because the Ka value is so small, for me the rule of thumb is 10 to the minus 4 or less. Then go ahead and try the x is small approximation. Now, you really should check whether this is true by replugging x and making sure that it's less than 5% of this concentration, 0.100. But well, maybe I'll double check, but not write it down. But anyway, since we're using the x is small approximation, that goes away. We have 1.8 times 10 to the minus 5 times 0.100 equals, and take the square root of that. Okay, x looks a little bit bigger than I thought it would be. X equals, let me do the calculation one more time. Nope, that was it. 1.342 times 10 to the minus 3 molarity. And to figure out if x is small is valid, it's that number, and it has to be 5% or less than this number. So I'm going to divide that number by the initial concentration, 0.100 times 100%, and the percentage is it's 1.34% of the original amount. Okay, is this thing auto-focusing again? Oh, it is. Okay, that is the concentration of H3O+. So right away, we can go ahead and calculate the pH. Take the negative log of that answer. Log of the answer times -1. And it starts out, no. Are we for real? It's negative. Is it really that acidic? I mean, if that's the number, that's the number. Okay, negative 0.127. Let me double check. 1.342 times 10 to the -3. Log of that answer. Oh, man, what happened there? Times -1. That looks much better. 2.87. I'm not sure what happened in the first pass at the calculation, but that looks better. 2.87. Okay, that is where it starts, right? The titration curve at 2.87. In the previous video, we had already gotten the pH for the equivalence point. I think it was 8 point something. Here it is. At the equivalence, it was 8.78. I'll mark that down. But do you see what other points they want? D and E. They want it before the equivalence, so here maybe, and for E at 15 milliliters above equivalence. Oh, so we do need to pick up, what was that volume, equivalence volume? Just in case we need it, that was 12.5 milliliters. Okay. D is tricky. What is the pH when 5.0 milliliters of KOH has been added? So this is before the equivalence, so maybe right there. Okay. Maybe I didn't emphasize it in an earlier video when we talked about the fundamentals of a weak acid strong base titration, but this area here is called the buffering region. It's buffering because we take some of the weak acid and convert it to conjugate base. And remember, when you have a solution with some weak acid and some conjugate base, that solution is a buffer. Why is that important? Because we're going to use that equation that's used to calculate the pH for buffers, which is the Henderson-Hasselbalch. But the issue is the concentrations of the acid and the conjugate base have to be determined based on the amount of base KOH that was added. So what we're really doing first is a stoichiometry analysis. Stoic analysis. Okay, and then we're doing a Henderson-Hasselbalch equation and solving for the pH. What is the stoichiometric analysis or stoichiometry analysis? The analysis is this. We started out with HC2H3O2 at 0.100 molar, but we're going to want to convert that into moles. And how do we do that? We started out with 25 milliliters. So we'll convert that into liters, 0.025 times molarity, which is moles per liter. And I get that. That is the number of moles that's in the Erlenmeyer flask, 0.0025. So this is 0.0025 moles. We are adding base, and the base we're adding is 5 milliliters of KOH, and we have the concentration of KOH. So now I want the KOH concentration, is 0.200 molar, but how many moles is that? How many moles is that? Oh, here it is. We added 5, right? We're adding 5 milliliters. So 0.005, so that's liters now, times 0.2. Okay, so we have 0.0010 moles. It's a strong base, so it is going to deprotonate this acid, and we're going to use all of the base because it hasn't reached equivalence yet. So we're going to have leftover acid because it hasn't reached equivalence yet here. That's where we have no acid, actually. Oh, well, no weak acid. But anyway, you see how we just have to subtract. Now, how do I want to show this? Well, we have an equation, and it gets that acid, or sorry, the base gets neutralized. And then we are left with C2H3O2 minus it. However much we convert this into its ions, we get the same amount of the conjugate base. So what's happening here? I like to call this a before, change, after table. I don't like calling it an ice table because we're not going to use Ka in this case. We're just doing a simple stoichiometric analysis. Because what's happening here is before any reaction happens, we have these amounts, and we have, well, this doesn't matter, but we have 0 here. Okay. How should I say this? I know we do have a little bit of this, but it's negligible based compared to what we're going to get from this interaction, because we're going to use up all of the KOH. You could think of it as we're going to lose all of the OH minus because that amount of OH minus is going to grab this hydrogen or this proton. So now we're going to lose acid, and we're losing the same amount. Okay, and this is plus 0.0010. So what's the purpose here? I know I'm going to put these numbers in just a bit. The purpose is Henderson-Hasselbalch. pH equals pKa plus log of the conjugate base divided by the weak acid. But these are the concentrations after that acid has interacted with the additional or the added KOH. You see how we're getting now different concentrations than what we had at the very beginning, before the titration happened. Anyway, what is 0.0025 minus 0.0010? So now we have 0.0015 moles of acid. We have 0 moles of base, right? That's what a buffer does. It neutralizes any little bit of added acid or base. Now, yes, we're not making a buffer or analyzing buffer, but this titration one last time before equivalence, that is buffering region. That solution, when you're below 12.5 base, acts like a buffer. This acts like a buffer, so it's resisting change. Anyway, what happened here? So if we used that much OH minus to neutralize that much H plus, what's left over is that, and we have exactly the same amount, 0.0010, same amount as the base. These are your new amounts. Now, the Henderson-Hasselbalch uses concentrations. So we do have to remember that we added 12.5. Oops, shoot. We added 5. Okay, so the new volume, it's a little bit tight. The new volume is 5.0 milliliters added to the original solution in the Erlenmeyer flask, which was 25.0 milliliters. 30 milliliters. So we are what? We are dividing by 0.030 liters. We're going to get molarity divided by 0.030. We have 0.05 molar. That number is going to be put here on the denominator, and we convert this into a concentration, 0.0010 divided by 0.030, and this one is 0.0333 molar. And we're going to put that in the Henderson-Hasselbalch. Now, think about what possibly could be the answer. It has to be higher than 2.87 because we added some base, but definitely it needs to be lower than the pH at equivalence because we're along this curve somewhere. Okay. I do need to start a new paper because I ran out of room at the bottom. Before we get to that new paper, we need pKa, but we were given Ka, so we could definitely get pK from that. And I'll do those calculations, and we'll plug in the numbers. Okay, pH equals pKa, log of 1.8 times 10 to the negative 5 times negative 1, because it's a negative log, 4.745. 4.745 plus log, and now we're using the concentrations, the new concentrations, right? And remember, it's conjugate base over weak acid. That over that. Okay. So we have 0.00, nope, 0.0333 divided by 0.050. You know, when your ratio is less than 1, that log is going to be negative. So we are going lower than 4.75, which is expected. Let's see how much lower. 0.0333 divided by 0.050, log of that answer. Okay, so there's your term for log of the ratio, and then we're adding 4.745. Ooh, so it's not that low. pH equals 4.57. Okay, it is definitely between these two numbers. Oops, 4. What was it? 4.57. Okay, so it's on this curve, maybe right there, right there. Is it the half equivalence? It's not. It's actually below the half equivalence. So at the half equivalence, remember the pH equals the pKa. Well, the pKa is that, and it is below half equivalence, so it makes sense that it is lower, 4.57. That is, again, the pH before we get to equivalence. Now E is fairly straightforward. We're adding excess base, right? We're above the equivalence. We're now up here, okay? Somewhere up here. Beyond 12.5. I said 15. Add 15 here. So, when you're above equivalence value, or volume, you have excess base, OH minus. All the weak acid has been neutralized because you're above equivalence. All the weak acid is neutralized. If we could figure out how much OH is in the solution after all that weak acid has been neutralized, then we could get POH, and then we could get pH. But the key is, again, we have a new volume, right? The POH is dependent on the concentration, so we need molarity. So let's take care of that first. total volume is you started out with 25 milliliters in the Erlenmeyer flask, plus I said add 15 milliliters of KOH. Okay, well, let's not put KOH. It's 15 milliliters of KOH, but we're calculating the total volume, 40 milliliters, equals 0.040 liters. So whatever moles we get for OH, we just have to divide it by this number. So what is happening here? We have HC2, H3O2. Okay, from part D, we said that before anything happens, it's that many moles. So let me put that 0.0025 moles. But now we're adding 15 milliliters of KOH. Okay, so KOH has its own concentration, 0.2, and we have 15 milliliters. So what do we want to do? We want to calculate how many moles. 0.015 times 0.2. Okay, do you see how it's more than the moles of acid? It's 0.00. It's not much more, but it is more. Remember, the equivalence volume was only 12.5, and we're just going up another 2.5 milliliters. So it's close, but definitely this is more. Okay, when these two react, again, you get the conjugate. No, what do you get? Okay, you get the water. Okay, yeah, let's do it this way. Let's just go ahead and solve for that. I wanted OH minus, but oh, we're going to get OH minus because look what happens here. When these two react, we're going to run out of the acid first, minus 0.025 moles, minus 0.0025 moles. You see how we go down to 0? Because we are past equivalence. We were able to neutralize all of the acid, and look how much base I have left over. 0.0030 minus 0.0025. Okay, I still have some base left over. I have 0.0005 moles. We're not even concerned about these two. Now you might say, shouldn't we be concerned about this? Like, aren't we converting all of this to the conjugate base? And doesn't the conjugate base make the solution basic? The amount of conjugate base, or I should say the amount of hydroxide ion that the conjugate base can produce is going to be so insignificant compared to the amount of OH minus that we're getting directly from the KOH. So we are just using this amount to figure out the POH. This is insignificant, okay? But I know that you know that when you throw the conjugate base in water, you get hydroxide ion, right? You get, oh, I don't have it on this sheet, but you basically do the base, right? Conjugate base plus water gives you hydroxide. But that number is so small, all we're worried about is this number. How much OH excess do we have? So when we convert to the molarity, remember our volume is now 0.040. This is my molarity, 0.0125 molar of KOH. Oh, and it's a strong base, so maybe we should call it OH minus, right? The POH. From the from the OH minus, we could get POH. Log of that answer times -1, 1.903, and then the pH is 14 minus that answer, 12.1. That's your pH. 12.1. So again, we are way up here, maybe in this part of the curve above the equivalence, and it's 12.1. Okay. The trick is, and we're done with E. The trick is knowing what are the steps or what are the key differences between solving for each of these. Let me go through these verbally, but jot them down, right? The equivalence volume, you're just trying to match the amount of base to neutralize all of the acid. So you could do that by moles, you could do it by, unit canceling, but ultimately you need volume of the base, You do have the moles of acid, right? And then you just have to figure out how much volume I need for this amount or molarity of base to neutralize that acid. B, C, D, and E. The questions where you're answering what is the pH. At the equivalence, I think this is the hardest one, B, because at the equivalence, you are converting all of your acid into the conjugate base, and then you're doing an ice table for that conjugate base, for the amount of conjugate base that you make, because the conjugate base will result in the acid again, and then OH minus. Okay, and then once you get the concentration of OH minus, you could get POH and then get pH. B is the hardest because you need KB, right? You need KB. And you need the KB and do an ice table. The pH before any base, that was easy. That was just an ice table that we've done before with any weak acid. So this is also an ice table. D, you are in the buffering region. You are in the buffering region. So what you need is to calculate the new concentrations, based on just simple stoichiometry, get your base down to 0, right? So figure out which was you can think of it as a limiting reactant, and make that 0. How much of the other partner did you convert? So I like to think of this as like a stoichiometry problem, and then Henderson-Hasselbalch, because you're in the buffering region. And then finally here, it's a stoichiometry problem, and you're just asking how much OH minus is left. Okay. All right. That completes this problem, A, B, C, and D. And once you answer all of those 5, then you could construct, right? You can construct your titration curve because you have the equivalence volume and you have 4 data points on the curve. All right. That's it for now. But again, that is a pretty sophisticated problem. You just need to practice.